Everybody. Today we're looking at the section 2.7 homework. So this is a lot of work with analyzing graphs of functions as well as piecewise defined functions. So we start out with problem 21 and just determining if this function is even, odd, or neither. And I'm seeing this symmetry about the origin. So if you flip that graph upside down, it's going to look exactly the same. So 21 is an odd function. 23 that looks like an even function because that graph is symmetric about the y-axis. If you fold that graph over the y-axis, it will fold on top of itself. So 31. So I'm just going to do some work here in 31. So here's the original m of x function here, and I want to create the negative. So for a, I need to find m of negative x. So I'm just going to replace every x with a negative x. So if I do that, this changes sign, and that goes here, because if you square a negative x, that's going to be positive x squared, but then 2 times negative x is minus 2x. So this is the m of negative x function. Negative of m of x is just multiply this whole thing by -1, and I get this here. And so I'm not getting, for part C, these are not equal to each other. So m of negative x is not equal to m of x, and m of negative x is not equal to the negative m of x. So C and D is no and no. So that means there's no symmetry. So again, if m of negative x equaled the m of x, that would be an even function. And if m of x equals the negative of the, if m of negative x equals the negative of the m of x, that would be an odd function. So this is going to be neither. That's 31. 35. Okay, so I'm just going to take this k of x function here. I'm going to replace the x with a negative x. This is going to change sign. This is going to change sign here. So I can pull out the negative out of the entire thing. So in this case, I am seeing that the k of negative x is equal to the negative of the k of x, because that's k of x right there. So since k of negative x is equal to the negative of the k of x, that's an algebraic proof that that is an odd function. 39. So I'm going to replace in the q of x function the x with a negative x. And if I do that, negative x squared is just back to itself. So it's equal to the same thing. So since q of negative x is equal to the q of x function, the original function, then that's an algebraic proof that that is an even function. Let's check out 47. Okay, so we have a piecewise here. And so we have to figure out is which piece do I put the x value in? Because a piecewise function is still a function. Every x value goes to one place. So for x values less than -1, I'm following the top rule. For x values greater than or equal to -1 but less than 4, I'm following the middle rule. And for x values greater than or equal to 4, I'm following the bottom rule. So part A, f of 3, I'm going to follow the middle rule. So that's 3 squared plus 3, which is 12. Part B, f of -2, I'm going to follow the top rule. So it's -3 times -2 plus 7, which is 13, and only 13. Part C, f of -1. So f of -1 is going to follow the middle rule. So that's -1 squared plus 3, which is 1 plus 3, which is 4. Part D, f of 4. So f of 4 is going to follow the bottom rule. So no matter what x value you put into that bottom rule, the y value is going to be 5. So for D and E, so any x value that you plug into the y equals 5 line, the y value is going to equal 5. Check 61. Okay, so now we need to graph a piecewise function. So first thing I need to do is graph the entire f of x graph. So here's f of x right here, the v graph, 0, 0, 1, 1, 2, 2, 3, 3, -1, 1, -2, 2. So this is the entire absolute value of x graph, but I don't want the entire absolute value of x graph. I just want this graph for x values less than 2. So I'm going to put an open circle right there for this piece. And then I'm going to graph -x plus 4. So I'm going to graph the entire -x plus 4 line, but then I'm going to erase everything I don't want. I'm going to start here at the point 2, 2, which is where this starts off. That's going to be closed circle, and then continue the line going to the right. And what's interesting about this is the same spot where one is an open circle The second one is a closed circle, so it connects like a train. So this is going to be a nice continuous function for problem 61. Okay, let's look at 62. Okay, so the 2x line, negative 2x line. Again, it's going to be the negative 2x line, but I don't want the entire negative 2x line. I just want the negative 2x line for x values less than 0. So that's going to be open circle and then everything to the left. But then square root of x for x values greater than or equal to 0. So that's going to be closed circle. So 0, 0, 1, 1, 4, 2. So this also will connect up. So this is open circle. This is closed circle. So I'm going to leave it all as one connected point right there. If you wanted to see this on the calculator, so we can put in negative 2x. Again, I always do a zoom 6 whenever I do a new graph. There's minus 2x. And if you don't want the entire negative 2x, we open a parenthesis, we put x, and then we go second math, which is test. Here's our symbols here. We go less than 0, close it, and then we get just that piece there. So that's matching up there. On y2, if I want to add the second piece, I'll do square root of x, and then open a parentheses, x, second math, which is test, greater than or equal to 0. So then I'll get my piecewise function there. And you can do it all on one line too. If you put a plus here, you can actually have this all on one line if you want to see it all as one function. But there's that right there. For 67, here's a nice piecewise of just line segments. So I want it just to be the negative 3. So y equals negative 3. The horizontal line y equals negative 3 from negative 4 to negative 2. So that's that piece there. It's going to equal negative 1 from negative 2 to 0. That's that piece there. And if you notice closed circle on this side because I'm including, open circle on this side because I'm not including. For this negative 3 one, closed circle because I'm including, open circle on this side. And then from 0 to 2 equal to 1, I'm going to go closed circle on this side, open circle on this side. And you can again do that on decimals as well. So we're going to do negative 3, and then I'm going to do squiggly brackets, and then what this one doesn't do is that open and close circle, but at least I can do negative 4 less than or equal to, so I'll do that, x less than negative 2. So this one just kind of does the pieces without the open and close circle. And then I can close that up, and then equals negative 1 from negative 2 to 0. Do squiggly bracket, negative 2. I do the less than and then hit equal, and automatically does that symbol for me, x less than 0. And again, without the open or close circle, we're seeing these pieces here. Close that squiggly bracket, and then it's equal to 1, 0 to 2. 1, squiggly brackets, 0, less than or equal to x, less than 2. There you go. So that same graph. Again, decimals isn't showing me the open and closed circle, so I would have to use my intuition. Like, am I including the point or not? And again, this is still a function because I'm passing the vertical line test because where one's closed, the other one's open. So there's some work with the piecewise functions. Let's jump to 89. So we're going to do increasing, decreasing intervals. For 89, I'm seeing this first section is decreasing. So from negative 3 to negative 2, that little function is decreasing, and then stays constant from negative 2 to 2, and then it's increasing from 2 to infinity because I see that open arrow. In 101, relative mins and maxes. Okay, so again, this is where they're real finicky, and you can't just write the point. The answers are actually the y value. So the local max is the highest point in a little area. So if you look at 0, there's a local max of 0 at x equals 0, because that y value of 0 is the highest y value in that little area around it. And there's some, even though like this graph continues up, So there's not going to be an overall highest point. And if you look at the y values of -4 that happen both right about -2 and 2, that would be local mins. Those are the lowest points in the area. So the answer to these questions are the y values. And then if you want, you can say at x equals -2 and at x equals 2. 108. Oh, good one here. So now we have to write the equation for the piecewise given the graph. So on that first piece looks like x squared. I'm seeing 0, 0, 1, 1, 2, 4. So there's no stretch or anything. -1, 1, -2, 4. Yeah, so that's the x squared graph. And I want that entire x squared graph, x less than or equal to 2. And then it's a horizontal piece. So y equals 4 for x values greater than 2. And you could have switched this. You could have just said this is x less than 2 and this is x greater or equal to 2. Since it connects up, it doesn't matter which one gets it as long as it's not both. Okay, let's do some of this concave up, concave down stuff. So just to start practicing this. So in 123, this little arc is salad bowl down and decreasing the entire time. So salad bowl down, concave down, and decreasing. 124 is salad bowl up, concave up, and increasing the entire time. 125 is salad bowl up, concave up, and decreasing from left to right. And then 126, that's salad bowl down, concave down, and increasing from left to right. So some new words here if you haven't seen it, the concavity. Okay, so 132, we're going to do this both on our calculators and in Desmos, just so you can kind of see the difference. So I'm given this goofy parabola. Again, let's do it in Desmos first. I can clear this out. So f of x equals just a really yucky one, -0.6 x squared plus 2x plus 3. Okay, so in Desmos, if I want to know, it's very quick and efficient because I can just do this and I can get that point and I can see that this parabola has a maximum value of 4.67 at x equals 1.67. So that's that max value, 4.67 at 1.67. This graph is going to be increasing from -infinity to 1.667, and this graph is going to be decreasing from 1.667 to infinity. So again, the increasing and decreasing are the x intervals. So that's very quick and easy to do on Desmos. That you can just use Desmos at home. If I use my calculator, so I'm going to put this function in here. So let's clear this out. So -0.6 x squared plus 2x plus 3. Again, I always do a zoom 6, zoom standard window to kind of see it. Okay, so now I need that point there. So second calculate, second trace, and then I'm going to get that maximum point right there. Now it's going to ask some questions, saying left bound, and it has my squirrel over here, so I'm going to move left and right. As long as I'm to the left of that max, I'm going to hit enter, and then I'm going to scoot it over to the right, and hit enter, and then my guess is going to be up here. Now I'm going to hit enter, and so that's my maximum value there. So there's my y value there, and then I can use this x interval to find, when it's increasing and decreasing. So here's a couple of the things you can do. If you didn't recognize these decimals, what we could do is quit out of that, and I can stow for x on this screen, and it brings that number over. Oh, there's a little rounding error, so it might not work. Let me see. Math fraction, yeah, a little rounding error, didn't work. In a lot of cases, it'll give you the number, and then you can math fraction it so that you can see the exact value. In this case, maybe I'll try it again, see if I can get it to be exact. Second, calculate, max. Sometimes it works, sometimes it's a little rounding error. We'll try it. Still maybe a rounding error, so let's try it though. We're going to store that number for x on the screen. Now a little rounding error. Math fraction didn't work. That's okay. But in a lot of cases, it'll bring this over, and then you can get the exact fraction that is, and then you can do alpha trace y1 of that x value. It'll give you that number there, and then if you could math fraction that, maybe this one will work. It worked. This one worked here. So that number that is the y value, that 4.6 repeating, if I bring that over, since I stored x on the solver screen, again, this x has nothing to do with the graph x. You can use any of these letters, all these letters in blue here, or in green, all these letters, A, B, C. The x one's right here, so it's quick to use. So I put this number here into the y1 function, and it gave me the exact number that I was able to math fraction it. So that's just something you can do. But again, there's those intervals, and this homework is complete. So hopefully you had fun. I'll see you next time in class. Take care, everybody.